So in this lesson, we are going to go ahead and discuss and prove what is known as the Chinese remainder theorem. But before we get started, I want to go ahead and do an example to motivate why we're going to be considering the Chinese remainder theorem and one of its computational aspects. So let us suppose we have two integers a and b, and first we are going to go ahead and assume that they are not divisible by 2. So in other words, a and b are both odd. And we want to prove that the difference of squares, a squared minus b squared, is always congruent to 0 mod 8. So how do we prove this? So the first observation is that if x is odd, then if we're reducing modulo 8, that means that modulo 8, we have that this is either 1, 3, 5, or 7 mod 8. So we have these three possibilities. So if we look at x squared, this is going to be either 1 squared, 3 squared, 5 squared, or 7 squared mod 8. But let's go through these. 1 squared is 1 mod 8. 3 squared is 9, reduce mod 8, we also get 1. 5 squared is 25, but 8 times 3 is 24, so we have 1 mod 8 as well. And finally, 7 squared is 49, but then we also have that 48 is a multiple of 8, so 49 is 1 mod 4. 1 mod 8. So in each of these cases, we get that the x squared is congruent to 1 mod 8. But now a squared and b squared are just arbitrary odd integers. So this here implies that a squared minus b squared is congruent to 1 minus 1 mod 8. And now this here is 0 mod 8. And so we got our answer. Similarly, if we had that a and b were not divisible by 3, then a squared minus b squared is going to be congruent to 0 mod 3. We get this by the same exact argument. If x is not divisible by 3, so that is, it's not going to be congruent to 0 mod 3, so then x is going to be congruent to either 1 or 2 mod 3. But if we square x, then we're going to have a 1 squared and a 2 squared mod 3. But 1 squared is 1 and 2 squared is 4, but 4 is congruent to 1 mod 3. So in both cases, we get that this is congruent to 1 mod 3. But a and b are just arbitrary integers, not divisible by 3. And so they're always going to be congruent to 1 mod 3. By what we have just shown. So we have that this is 1 minus 1 mod 3. So we have that this is congruent to 0 mod 3. So if we now look at the next statement, now we're going to go ahead and suppose that both a and b are not divisible by 2 and 3. Then a squared minus b squared is congruent to 0 mod 24. Now for this one, we know from the first statement that we proved that is congruent to 0 mod 8. So we have shown that a squared minus b squared is congruent to 0 mod 8. And we have also shown that a squared minus b squared is congruent to 0 mod 3. So this tells us that a squared minus b squared is equal to 8k for some k. And the bottom one tells us that a squared minus b squared is equal to 3l for some l. And so in other words, we have that 8 and 3 are factors of a squared minus b squared. And so consequently 24, because these are relatively prime, 24 divides a squared minus b squared. So what we have just shown is that anytime we have a difference of squares, if a and b are relatively prime, they are always going to be divisible by 24. But what the Chinese remainder theorem will allow us to do is in one step go from having the deduction for this and this to the fact that this is divisible by 24. And so this intermediary step of having to go at the factors and arguing it from this point of view will be eliminated. But the Chinese remainder theorem is also going to have many applications of theoretical importance which we will use throughout the course, and I'll talk about them in just a moment. But first we're going to go ahead and prove the Chinese remainder theorem. So this is due to Sun Tzu in the 300th, around 300 Common Era. Common misunderstanding is that Sun Tzu is the same author as The Art of War. It's actually two different people. So not the same person who wrote The Art of War, but that's oftentimes something that is referenced. And so what it says is that if a and b are relatively prime natural numbers, and k and l are integers, then there exists an integer s such that s is congruent to k mod a, and s is congruent to l mod b. And so here we're using the fact that a and b are relatively prime. And this solution is going to be unique modulo a times b. Now, something I want to point out is this is in the language of modular arithmetic. That was done by Gauss. And so this is not the same statement that Sun Tzu wrote down over 1700 years ago. Instead, we are actually covering an equivalent formulation that is due to Gauss that appeared in his Discusiones Arithmeticae in 1802. So how do we prove this? The proof of this actually goes to techniques of Diophantus that we have covered, specifically Diophantine equations and their solutions. So the way we're going to go about this is by considering the following. So consider the Diophantine equation ax plus by is equal to L minus k. So what do we know about this Diophantine equation? We know that the coefficients are a and b, but they are relatively prime. And we know that a Diophantine equation of this form has a solution if and only if the GCD of a and b divides the right-hand side. But the GCD is 1, and that always divides L minus k, so this has a solution. So since a and b are relatively prime, this Diophantine equation, which I'm going to abbreviate to DIO, an equation, has a solution. And so let's go ahead and call that solution x comma y, but now in lowercase. So that is, our equation is ax plus by is equal to L minus k. Now, let's go ahead and add both sides by k and subtract by. So specifically, we're going to have ax plus k. We added k on both sides, but we're going to be subtracting by on both sides. And so we have L minus by. And we're going to go ahead and set this equal to s. So let's go ahead and define this to be s. And so we have this. Now, if we reduce the quantities modulo a and b, what do we get? So then, s, if we look at, so we know that these are equalities. If we reduce this one over here, mod a, we get that this here is going to be congruent to k mod a. If we look at now this equation here and reduce it by b, we get L. And we got this. So we are now done with the first part of this Chinese remainder theorem. We have shown that there is an integer s namely this integer here that these are both equal to, and we have these congruences. So let us prove now uniqueness. So this shows existence. Of S. For uniqueness, what we are going to do, so we want to show that this is unique modulo A times B. So let's suppose that we have another solution. So suppose that S naught is any other solution. Actually, any solution, let's not say other, because it could be the same, which is what we want to show, is any solution to the system of congruence, to the system of congruences. So what I mean by this is that we have that S naught satisfies the same conditions that S does. So that is, S naught is congruent to K mod A, and S naught is congruent to L mod B. Now, these are all congruences, and so we have S naught is congruent to K mod A, but S is congruent to K mod A. Since congruence is an equivalence relation, we get, so since congruence is an equivalence relation, we get that S minus S naught is congruent to, oops, I'm jumping ahead, that this here is congruent to S naught mod A, so transitivity, and S is congruent to S naught mod B by transitivity. So therefore, subtracting, we get that S minus S naught is congruent to 0 mod A, and S minus S naught is congruent to 0 mod B. So thus, A divides S minus S naught, and B divides S minus S naught. But what we want to show is that S is unique, that the solution S and S naught are unique up to modulo A times B. So where do we go from here? So we know that A and B both divide S naught minus S. So what that is saying is that the least common multiple of A and B also divides S naught minus S. So from here we get that the least common multiple of A and B divides S minus S naught. So we have this. And now we use a nice theorem that we have from our section on the fundamental theorem of arithmetic, which is if A and B are relatively prime, then we can conclude in this case that the least common multiple of A and B is A times B. So since the GCD by assumption is 1, we have that the least common multiple of A and B is equal to A times B. So this is from lesson 5. So now we have, so therefore, we have now that S minus S naught is congruent to 0 mod A times B, which implies that S is congruent to S naught mod AB, which shows the uniqueness up to congruence modulo A times B, and that finishes off the proof. And so now we are officially done with this statement. For our next statement, we're going to go ahead and consider the general version of the Chinese remainder theorem and its statement, but we will not prove it. This will be left as a homework assignment. But the proof follows similar to the previous one, but we have to loosen our restrictions. And the main loosening of the restriction from the last statement is that we're dropping the assumption that we had a and b being relatively prime integers. And so specifically, we're looking at a and b. They are now just any natural numbers, and k and l are integers. And what the general version says is that there is a integer s satisfying these two congruences if and only if the GCD of a, b divides L minus k. So when you prove this for the homework assignment, just keep in mind that when we set up the general version of the Chinese remainder, when we proved the Chinese remainder theorem in its original form, we considered that Diophantine equation ax plus by equals L minus k. As a consequence, this has a solution if and only if the GCD of a and b divides L minus k. And so that is what is happening here, is that that's coming from the solution set, the if and only if condition for solutions to a linear Diophantine equation. And so from there, you can go about the proof in the same manner we just did, but there are some restrictions. Because we no longer have that it's relatively prime, the solution won't be unique up to a times b, but up to the least common multiple of a and b. So it will be unique modulo the least common multiple of a and b. And so that's what you'll be doing for homework. So before we continue, we're going to be doing many computational examples for the remainder of the lesson, and then we're going to finish off with a theoretical application. But I should mention that in the textbook, you can read up on applications of the Chinese remainder theorem for understanding the Mayan calendar. So you'll be able to find this in section 7.6 of the textbook. The Chinese remainder theorem is also very useful in cryptography. And in this course, at the end of the term, you have a final project, and one of the possible options you can choose is cryptography. And so this is something that you can investigate in further detail. But from a theoretical aspect, which is how we're going to be approaching it for the rest of the course, we're not going to be as we're not going to necessarily care about its computational manifestations, but more of its theoretical implications. And so that's something that we're going to be seeing throughout the term, especially towards the end. And so the Chinese remainder theorem plays an important role in the foundational results of what today is known as algebraic number theory. And in a general proof that Kummer did for Fermat's theorem in 1847 for specific primes, known as regular primes. And so this was essentially the foundations for these results, for this result here. And we will be seeing the theoretical application of the Chinese remainder theorem next week when we prove some of the properties for the Euler phi function that generalize Fermat's little theorem, which will be the topic of Monday's lesson. So let us go ahead and now do an actual example with the Chinese remainder theorem. So here we have s is congruent to 4 mod 5 and s is congruent to 1 mod 2. And we want to know if this s exists in relation to the statement of the Chinese remainder theorem. And we want to find if it does, we want to find the least possible solution in terms of the positive integers of this solution set. So how do we do that? Well, let us go back to the proof, because the idea of how we argued it is that it's all constructive. It gives us the algorithm for doing this. Step 1, write ax plus by equals L minus k. So that's our very first step. So let's go ahead and write that algorithm down. So here's the algorithm. By the proof, we have that we're looking at the Diophantine equation ax plus by equals L minus k, and then the proof tells us that the s is attained by considering s is equal to ax plus k, which will also equal L minus by, where little x and little y is a solution to the Diophantine equation. Something to note is when finding solutions to Diophantine equations, we do have Blankenship's method at our disposal, and we did questions along these lines during the first week. So let us go ahead and get some practice with computing this. So we're going to be looking at this exercise. So I'm going to rewrite it over here. We have s congruent to 4 mod 5 and S congruent to 1 mod 2. If we label this, so we have here K, here's A, and then over here we have that 1 is L, and B is 2. So we have this. So our Diophantine equation that we want is 5x plus 2y is equal to L minus K, which is 1 minus 4, negative 3. So we want to find a solution to this Diophantine equation. But before we move on, I just realized I skipped ahead. The exercise is asking us, does S exist? In this case, it does, because we're looking at 5 and 2. These are relatively prime, so the Chinese remainder theorem applies. If we have relatively prime integers a and b, then we always have that there is an integer s that satisfies these congruences. So let's go ahead and find a solution to this Diophantine equation. We could approach this in the same manner that we did when doing linear Diophantine equations a couple weeks back. But in this case, we can do it by inspection. We know that we want to find a solution so that we get back negative 3. But we can do that by letting x equal to negative 1. So that will give us negative 5, and then put a plug in y equals to 1, and we have negative 5 plus 2 equals negative 3. So let's observe that I'm going to use the little notation. Little x and little y equals negative 1 comma 1 is a solution. So now step 2 tells us that the solution we want is S, which is going to equal AX, so in this case 5 times negative 1 plus K, which is 4. But we could also do it, and this is something just to be good to do just for checking and making sure there's no arithmetic errors. We should also get back the same exact answer if we did this with L minus by. So if we did this with L minus by, we will have 1 minus 2 times 1. But in both cases, of course, we have that this here is going to give us back negative 1. And so that's going to be our value for S. And this is unique. So this is our S. So we know that S, so by Chinese remainder theorem, S is unique modulo A times B. So in this case, 2 times 5, which is 10. So since negative 1 is congruent to 9 mod 10, 9 is the least positive integer satisfying the system of congruences. And we're done. Also, because we know that this is unique modulo 10, we can go one step further and give all the possible values of S. It's just those values whose remainder is 9 modulo 10. So I'm going to put this in a box here. So the desired set of all solutions S is the set where we have 9 plus 10 k. K is an integer. And so we see here that if we plug in k equals to 0, we get back 9, the least element. If we plug in k is equal to negative 1, we will have 9 minus 10, which gives us back negative 1, which was the value for S that we initially got. And so that finishes off for this one. So let's do several more examples. So for our next example, we're going to do a more involved question. So here we're going to need to utilize the general version of the Chinese remainder theorem because the question given tells us to find a integer s satisfying the following congruences. S is congruent to 1 mod 16 and s is congruent to 3 mod 6. But now 16 and 6 are not relatively prime, so we can't apply the Chinese remainder theorem, but instead need its general version. So with the general version, we remove that restriction of having that a and b are relatively prime. But aside from that, the argument, if the s exists, which it will for this example, we then proceed exactly as we did before. We find a solution to the Diophantine equation. Once we have a solution to the Diophantine equation, we have the value s. And then we know that it's unique modulo the least common multiple of a times b. So let's go ahead and do this one. So first thing, I'm going to go ahead and write these congruences down. So instead of writing them down, let's go ahead and just label them down. So we have s is congruent to 1 mod 16. So our 1 is going to be k, the 16 is going to be a, the 3 is going to be l, and the 6 is going to be b. So we're looking at the Diophantine equation. So want to find a solution to the Diophantine equation 16x plus 6y is equal to L minus k, which is 3 minus 1, is equal to 2. But now notice that the GCD of 16, which is 2 times 2 times 2 times 2, so 2 to the 4, and 6, which is 2 times 3, so the GCD is just going to be 2. So Blankenship's method gives a solution to this. Method gives a solution. So let's go ahead and compute that solution. I'm going to go ahead and do it down here. So what we have, we start off with our matrix. And actually I'm going to zoom in over here. So we're going to start off with, actually before we do the matrix, so remember that when applying Blankenship's method, we really want to apply the Euclidean algorithm. So we have 16, 16, and we're dividing this, we're going to divide 16 by 6. Now if we do that, we have that the remainder of 16 modulo 6 is going to be 4. And so we're going to have 16 times 2 plus 4. Then we go ahead and apply Blankenship's method again, but this time around to 6 and 4. So the remainder. But now in this case it's just 4 times 1 plus 2. And so we have this here. And then if we apply it one more time, of course, we're going to get 0. So we're going to have 4 is equal to 2 times 2 plus 0. So we got that. And so this is going to motivate the steps for Blankenship's method. So I'm going to go ahead and just bring this over to the top. So as a reminder, when applying Blankenship's method, we know that the quotient here is 2. So we want to do we're going to start with the second row and we're going to be doing minus 2 times the second row and then adding it to the first row. And then we're going to replace that with and then that will be the first row replaced. So this here stays the same. This is 0, 1, and 6. We multiply by a negative 2 and add. So this is going to stay 0. Oh, sorry. That's going to be 1 plus 0 plus 0. Then we have 1 times minus 2 plus 0. So we have a minus 2 here. And then we're going to have 6 times negative 2 minus 12 plus 16, 4. And so we have this. Now we apply Blankenship's method again, but now the next quotient is 1. So we're going to multiply the first row by negative 1 and add it to the second row, and that will replace the second row. So now we have the first row it's going to stay the same, so 1 minus 2, 4. We multiply by negative 1 to the first row. This will give us a minus 1 for the lower left. Then negative 1 times negative 2 is positive 2. Added to 1, we get 3. And then we do -1 times 4, -4 added to 6, we get 2. And so we have this here. One last time. Now the quotient is 2. We're going to go ahead, multiply now the second row by -2. Row 2 added to row 1, replace row 1. And so now this gives, the second row is going to stay the same, so I'm just going to copy it down, -1, 3, 2. And then we're going to have -2 times -1 is going to give us +2, then we get a 3 here. -2 times 3 is going to give -6, plus -2 minus 8. And then -2 times -2, of course, -4, 0. And so we're done here, so we got this. But now to get blank interest method, we want to interchange. So we want the 0 on the bottom right. So we swapped 2 rows. So we have our solution is x is -1 and y is 3. -1, 3. So now s, so by step 2, we know that now s is going to be ax, and so here we have 16 times -1 plus k, and then this should equal the same as doing L minus by, so we have 3 minus b, which is going to be 6, times 3. And so we can see here that we have -16 plus 1, -15, which is the same as what we get on the right-hand side, because we're going to have 3 minus 18. And so this is just a sanity check that we get both values to be correct on both sides, so we know that now for sure this is the value we want. So we have that s is -15. This is unique. Modulo the least common multiple of a and b, which is 16 and 6, but now that is going to be 48. So we get this here. And so what we want to do now is find the set. And so the set of solutions is going to be capital S. Oh, actually, let's not use S. Let's use T. This is going to be the set of solutions -15 plus the least common multiple, 48. K. Oh, and K is already being used, so let's not use K either. Let's go ahead and call this U, where now U is any integer. And so we have our set of solutions. And if we want to find the least solution, the least positive solution, we go ahead and add 48 to 15, and we get back 33. So 33 is the least positive solution. And so now that concludes it for this example. So for our next example, we are going to go ahead and consider the following. We're going to let x be 3,100,997,996, and we want to find what this number is modulo 90. Now, we know that we have tests for congruence modulo 9 and 10, and so instead of going about this and figuring out what the remainder of this number modulo 90 is, we're going to build it from only knowing what is happening modulo 9 and 10. And that's how the Chinese remainder theorem makes its usefulness from a computational point of view. You have these large numbers, but we can reduce it down to just the smaller factors. And if we understand that there, we can then glue it to get the product, in this case 9 times 10. So let's do this. So from Friday's lesson, we have the following. So last Friday, we saw that x modulo 10 is the same, 16. So this modulo 10 is the same as the singles digit, so this is just going to be 6. So this is just x congruent to 6 mod 10. And if we're looking at it mod 9, well, if we're looking at it mod 9, we just have to go ahead and add all the digits. Then x will be congruent to 3, plus 1, plus 0, plus 0, plus 9, plus 9, plus 7, plus 9, plus 9, plus 6, mod 9. But the benefit here is that we have 3 plus 1, 4. And now the 9s go away, and then we just have 4 plus 7 plus 6 mod 9. But now this here is going to be equal to 8 mod 9. And so we got our congruence modulo 9. And now we want to apply the change remainder theorem. So how do we go about this? So here's how. The way that we're setting this up is we want to have, in the notation that we have for the change remainder theorem, we have S. So we want to find S congruent to 6 mod 10 and S congruent to 8 mod 9. 10 and 9 are relatively prime, so change remainder theorem tells us that there will be a solution, and it's unique modulo a times b, 90. So that's the desired answer. If we find S, we are done. So we go ahead, apply change remainder theorem as we have done. So here we have K, A, and over here we have L and B. We create our Diophantine equation. We're looking at the Diophantine equation 10x plus 9y is equal to L minus K. So in this case, 8 minus 6. And so here we have that this is going to be 2. And so we want to solve the Diophantine equation 10x plus 9y is equal to 2. Now, in this case, we can do this by inspection quite easily. If we do 10 times 2, that's 20. Multiply 9 times negative 2, we get 18 negative. So 10 minus 18. 20 minus 18, we get 2. So we have that little x and y equals to 2 comma negative 2 is a solution. So that means that now S, which is equal to AX plus K, is going to be the desired solution, so 26. And just to make sure that we did everything correctly, this should equal L minus BY, and so we have that this should equal L minus 9 times negative 2, and so that right there gives us positive 18 plus 8. We also get 26, so good. So we got our answer. And so now by the change remainder theorem, we have that the solution we want. So S equals 26 is unique modulo 90. But the way we set this up was by looking at the values for x, the large number. And so what we now have is that x, so therefore x is congruent to 26 mod 90. And so now we have gone ahead and computed this using change remainder theorem. But we never really computed with the large number, but instead reduced this mod 10, 9. That was simpler. We got that this was equal to 26. And because it's equal to 26 by the construction, which was from looking at x congruent over here, we know now that x is going to be congruent to 26 mod 90. So for our next statement, we're going to come back to what we discussed at the beginning of today's lesson and make that technique precise. So specifically, we showed that if a and b are integers not divisible by 2 and 3, then we have that the difference of squares, a squared minus b squared, is always divisible by 24. And we proved that by relying on congruence modulo 8 and congruence modulo 3. And that told us that we have divisibility by both of them. So we have 8 and 3 in as a factor, so it's divisible by 24. But now, this observation here makes that statement precise in generality. So what this says is that if we have natural numbers a and b that are relatively prime, and x, y are integers, then x is congruent to y modulo a times b if and only if x is congruent to y mod a times b and x is congruent to y. X is congruent to y mod a and x is congruent to y mod b. So let's go ahead and prove this. So the proof goes as follows. So first suppose, so we're going to do the forward direction. So suppose that x is congruent to y mod a times b by theorem 1.7.1. This is the theorem on equivalent conditions. So EQ is equivalent. Conditions on congruence. We have that there exists some integer k, such that x is equal to y plus a times b times k. But if this is the case, we can reduce mod a and mod b. And doing so gives what we want. Because now we get x is congruent to y mod a and x is congruent to y mod b. And that completes the forward direction. Before we move on, did we use the GCD of a and b being 1, which is part of our assumption? The only thing we used was theorem 1.7.1 and then reduced. That was never assumed in our proof. And the reason I'm emphasizing this is that this proof works in general. It does not require the assumption that the GCD of a and b is 1. The reason it's here is so that we can prove the converse. So for the converse, we need to change the remainder theorem, which assumes that a and b are relatively prime natural numbers. So let's go ahead and prove that. So converse. So suppose now that x is congruent to y mod a, and x is also congruent to y mod b. But this is just the statement of the Chinese remainder theorem. We have that S is x, k and l is y, and now the Chinese remainder theorem tells us that this is a unique solution modulo a times b. And so here this is where we use the fact that we have relatively primeness. Oops, 1 second. Erased. That's odd. Sorry about that. So, since the GCD of a and b is 1, the Chinese remainder theorem implies that x is unique modulo a times b. So how do we get that x is congruent to y mod ab? Well, that comes from just doing the following. But we also have that y is congruent to itself. So y is congruent to y mod a, and y is congruent to y mod b. by uniqueness of solution. So y here is playing the role of the S naught in the change remainder theorem. So by uniqueness of solution, I should write. Of solution, we have that x is congruent to y modulo a times b, which completes the proof. And so now we are done with the statement. And this actually generalizes as follows. And this will be part of your homework assignment. And so what we have is that if a1, a2, all the way to ar are natural numbers that are pairwise relatively prime, and x and y are integers with the property that x is congruent to y modulo the whole product of those, then that's equivalent to having the congruences on the right hand side, where we have now these arc different congruences. And that's what we were doing when we were considering the situation of a squared minus b squared being divisible by 24 whenever a and b are not divisible by 2 and 3. So here's how. So we already showed at the beginning of today's lesson that a squared minus b squared is congruent to 0 mod 8, and a squared minus b squared is congruent to 0 mod 3. And so now what we are doing is going from here over to here. And so a squared minus, since 8 and 3 are relatively prime, we have that a squared minus b squared is congruent to 0 mod the product of 8 times 3, 24. And so now we are done with that statement, applying it from the point of view of the chain remainder theorem. So for the next exercise, we're going to go ahead and consider the equation 4x congruent to 16 mod 18. And we want to solve for x with the property that x is greater than or equal to 0 and less than or equal to 17. Now, this question can be done in various ways. In the lecture notes, I have provided 3 different solutions, but I'm going to go ahead and do this via the chain remainder theorem. But before we get started, I want to make a connection to the last lesson. So the last lesson concerned looking at multiplicative inverses, and we started the lesson by considering one of the homework questions regarding fill. And so with 4x congruent to 60 mod 18, we cannot solve this by just multiplying both sides because 4 and 18 are not relatively prime. So we cannot multiply both sides and then deduce that this is x, that I cancel off the 4 and then solve for that. So we cannot do it via the techniques from multiplicative inverses. But the chain remainder theorem will actually allow us to reduce this to multiplicative inverses. Here's how. So we're starting off with 4x congruent to 60 mod 18, but for the chain remainder theorem, we want to break that up into 2 relatively prime factors. So we're going to go ahead and take 9 times 2 is 18. Then we look at the equation 4x congruent to 16 mod 9 and 4x congruent to 16 mod 2. Now 4x congruent to, so 16 modulo 9 is 7. And 16 modulo 2 is just 0. But I want us to now investigate what's happening on the right hand side. We have 4 times x is 0. So what solutions work for x? Well, we can plug in 0, that works. We can plug in 1, that works because we'll just have 4 mod 2. And so the key thing is, on the right hand side, because this is 0, and we have a factor of 4 in front of it, when we reduce mod 2, this is just always going to be 0. So in other words, finding the solutions for x only depends on the mod 9. So if we solve this congruence, we are done. So even though we use the Chinese remainder theorem to focus on this end, we actually will not have to invoke Chinese remainder theorem at the end because we're getting the congruence from this here. So let's continue. So now we're looking at 4x congruent to 7 mod 9. To solve this, we want to go ahead and multiply both sides by 7. Because if we do 4 times 7, this is going to be 28. But 28, if we look at this mod 9, 27 is 9 times 3. So this is 1 mod 3. So in other words, 7 is the multiplicative inverse to 4, modulo 9. So now we multiply both sides by 7. This is equivalent to saying just x is congruent to 49 modulo 9, but 49 is 4 mod 9, because 45 is 9 times 5. And so we got our solution. We have that this is just going to be x congruent to 4 mod 9. And now we got our final answer because we know that this here will always be satisfied. Now, but to finish this off, we want to find all the solutions. It's not just 4, but also our solutions are going to be, all solutions are of the form, so they all have to be congruent to 4 mod 9. And so we're looking at the solution set 4 plus 9k, where k is an integer. But now, if we want to only look between x being greater than or equal to 0 and x is less than or equal to 17, that gives us that the solutions we want are just 4 and 13, since 13 mod 9 is 4. And now we're done. For our last statement, we are going to prove a generalization of the Chinese remainder theorem, which gives us that two sets are equinumerous. And this statement is going to be the recurring result that we're going to be invoking for some of the theoretical results that we will see later in the course. So what does this say? So we have natural numbers m and n that are relatively prime, and it just simply says that the following function is bijective. We are going from the integers modulo m times n to the Cartesian product of the integers modulo m times the with the integers modulo n, where we go ahead and define this with f of a bar goes to a bar comma a bar, and I'm going to make a note about this notation in just a moment. But what I want to emphasize is that it allows us to do, why it's connected to the Chinese remainder theorem, is that it's telling us that if we are looking at the integers modulo m times n, that's a larger ring. It's easier if we just work modulo m and modulo n, which is what we have been doing. And so this is actually generalizing the Chinese remainder theorem. The notation is what we first need to get over, because we have this a bar notation and it really is an abuse of notation at this point. Up to this point, when we refer to a bar, there's always just one ring. We are working with the integers modulo n. So there's no ambiguity as to what the congruence class of A is. But now there is. We are working with 3 rings. So we have that this A bar is a congruence class here. This one over here is a congruence class here. And this one here is a congruence class here. And so what I'm going to do to avoid any confusion is rewrite this statement as follows. So instead of having A bar by itself, to emphasize where that congruence class lives, I'm going to write m times n. And then what this is saying is that then a bar, that this is equal to a bar mod m, comma a bar mod n. And so that's what this statement is getting at, and that way we have no confusion as to where which congruence class lives. So let's prove this. We want to prove the function is bijective, but first we need to prove that it's a function. In other words, we need to prove that f is well defined. So we first show that f is well defined. So to do this, let us suppose that a bar mod mn is equal to x bar mod mn. So recall that whenever we say well defined, what we are saying is if we evaluate the function at a bar and then evaluate it at x bar, we better get back the same exact output, because to be a function, every input must go to the same exact output. But we're working with congruence classes, so we need to make sure that that is the case, that this is independent of representative. So how do we go about this? We have this equality by the theorem on the equivalent conditions of congruence. So this is theorem 1.7.1 in the lecture notes. So equivalent conditions on congruence. We have that there exists an integer k such that a is equal to x plus k times mn. And so we have this. Then we have that a is congruent to x, and so we're just doing the same exact argument we just did a moment ago for one of our earlier results. And so we have a is congruent to x mod m, and a is congruent to x mod n. Therefore, evaluating at a bar mod mn is the same as evaluating at x bar mod mn, because the output is going to be a bar mod m, and then for this one it's going to be x bar mod m. But we know that a and x are both congruent mod m, so they're the same exact congruence class. So we got that the first ordered pair is the same, but the same argument holds for n. So we do have that this here is an equality. So that shows that this is well defined. So f is well defined. So now it remains to show that it's one-to-one and onto. Is one-to-one and onto. So let us go ahead and show injectivity first. So for injectivity, let us suppose that we have that. So next we show injectivity. So f is one-to-one. So to this end, suppose that f of a bar mod mn is equal to f of x bar mod m times n. Now, this is equivalent to having the ordered pairs being equal. So this is saying a bar mod m times n. Oops, sorry. This is saying that a bar mod m is equal to x bar mod m, and a bar mod n is equal to a bar mod n. But we know that m and n are relatively prime. Is equal to 1. We have the corollary. So by corollary to CRT, so this is the statement that we just proved. This is 193. So by corollary 1.9.3, we have that a bar let me write it as, let me take this few steps. So A is, we have that here, since A is congruent, so this statement here is saying A is congruent to X mod M, A is, ooh, typo. That's X bar, sorry. So we have that this statement here is saying that A is congruent to X mod M, A is congruent to X mod N. The corollary we just did for the Chinese remainder theorem now tells us that A is congruent to X modulo Mn, which tells us that now they're the same exact congruence classes, mod Mn. And so in the notation that we're using here, we get this. Oops, and I get typo again. That's X. So this shows that F is injective. And so now we have shown that this is an injective function. Before we continue, I want to draw your attention to the corollary 193 again. So what we have just done for our proof is just do this again. We're using this if and only if. So what we actually have just done is show the equivalence of one-to-one and well-defined, because we started off by saying if X and Y are both congruent, then we have these congruences. That was the well-defined aspect. The backwards direction is being injective. If we have that X and Y satisfy these congruences at the ordered pairs, then X and Y is congruent to A times B. So this is just to emphasize why we call it a generalization of the Chinese remainder theorem, is that we really have just packed into it the proof that we did for corollary 1.9.3. So all that remains for us to show is that the function is surjective. So to show that it's surjective, we need to choose an element in the codomain, in the set of outputs. So we're going to choose an ordered pair here. So for surjectivity, let X bar mod M and Y bar mod N be an element, any arbitrary element of the integers modulo N, Cartesian product, integers modulo N. And what we want to do is find an element that maps to both of these. And now for this, we're going to go ahead and use the Chinese remainder theorem. Because by the Chinese remainder theorem, so specifically since this is crucial, so we are here again using the GCDE of M and N is 1. There exists an integer S such that S is congruent to X mod M and S is congruent to Y mod N. And so we have this element, and this is unique. Moreover, S is unique modulo the product of M times N. So we have M times N here. So now what we have is that therefore, if we now apply the function f to the congruence class of S, so we take f of S bar, but now we're working in the congruence class for M times N. This is going to map to the congruence class, oops, I did not mean to write function, to the ordered pair S bar mod M S bar mod N. But what we just said with the congruences over here from the Chinese remainder theorem is that S bar is equal to X bar modulo M, and S bar is equal to Y bar modulo N, where whenever I say bar is with respect to the corresponding N or M that we're modding out by. And so here we have that then this here, the very first entry in the ordered pair, would be equal to x bar mod m, and the second entry is going to be y bar mod n. So the function is surjective. And so therefore the function is bijective. So I'm going to finish it off. So I've run out of space. So I'm just going to come up here and finish. So f is onto, and thus bijective. And we're done. And so next week, when we prove Euler's theorem, this is going to be one of the crucial ingredients for proving it. And so this is what I meant earlier, that the Chinese remainder theorem is of important use from a theoretical point of view, is the fact that we have this bijection of rings. And for those of you who have taken abstract algebra, you can actually show, now we've already shown this a bijection, but this actually is a ring isomorphism. And so we're going to be seeing this throughout the term pop up for some of our results.